Welcome to Geology 108, Water World. Water is an essential ingredient for all living organisms. The accessibility of water in liquid form is essential for sustaining life as we know it. Whether life, and perhaps intelligent life, has appeared on other planets depends on the availability of water. At first look, Earth seems pretty unique in the solar system by the presence of water in three different states: liquid, vapor, and ice. However, water is one of the most abundant chemicals in the cosmos. The more we look, the more we find it, and its presence on other planets, moons, and comets provides clues to its abundance on Earth, as well as the possible distribution of water-dependent life in the universe. Following the first supernova, as space was seeded with a variety of new elements, many interesting molecules could finally form. Water, the molecule H2O, made of 2 hydrogen and 1 oxygen atoms, is one example. We know the average composition of the solar nebula. That is, the average composition of the solar system, thanks to the numerous meteorites that land on Earth. The oldest meteorites provide an estimate of the age of the solar system. They date back to 4.5 billion years ago. There are many types of meteorites depending on their origin and the type of celestial bodies they represent. Chondrites represent the material in the solar nebula before formation of the sun and the surrounding planets. About 85% of meteorites that fall on Earth are chondrites, and we have so far 27,000 known specimens. Achondrites represent differentiated material with a composition similar to that of terrestrial planets. In many respects, the average composition of chondrite meteorites closely matches that of Earth today. For example, the proportions of oxygen, silicon, aluminum, magnesium, calcium, and iron are remarkably similar. But compared to chondrites, volatile elements are missing from today's planet Earth. The most primitive chondrites average more than 3% carbon, but all the known carbon reservoirs on Earth now add up to less than 0.1%. Similarly, the water content of chondrites is much greater than Earth's modern average, perhaps 100 times more. We can draw two important conclusions from this observation. First, most of Earth's volatiles must have been lost to space or are deeply buried, far beyond our ability to sample. This is compatible with all the terrestrial planets having been stripped of their primordial atmosphere. Second, it means that the Earth is on average much, much drier than the rest of the solar system. This indicates that water must be available in profusion elsewhere in the solar system and elsewhere in the universe. There is no large standing bodies of liquid water on the surface of Mars. But Mars has a lot of water, most of which occurs as subsurface permafrost and maybe some groundwater in even deeper zones. A subglacial lake was recently discovered 1.5 kilometers below the southern polar ice cap. It is the first known stable body of liquid water on Mars. These hidden repositories are potentially huge. Almost all water on Mars today exists as ice. If thawed, it will cover the whole planet to a depth of 35 meters. But there are many clues in the landscape that point to free-flowing water at the surface of Mars in its distant past. Before 3.8 billion years ago, Mars may have had vast amounts of liquid water on the surface, including an ocean covering a third of the planet. This video shows an animated flyby of Valles Marineris, the largest canyon on Mars and in the entire solar system. The animation glides over impact craters along the plains and flies over a deep trough, its cliff faces scarred by many landslides. In some parts of the valley, water-bearing minerals have been detected, suggesting that significant quantities of water may have once flowed there. These and other evidence indicate that water once flowed freely across the sculpted Martian surface. One continuous ocean may have covered most of the northern latitudes, more than a third of the Martian surface, to a depth of 550 meters. It is quite possible that Mars may have been a blue ocean-covered, life-giving planet many million years before Earth. Whatever water Mars has left, it is a lot less than the way it started. Gravity, or rather the lack thereof, is the culprit. Mars is too small to hold onto its hydrogen. Even though water molecules evaporate, they are a bit too massive to just fly off into space. The trouble is that cosmic rays split the water in two, forming one hydroxyl molecule, OH-, and one hydrogen atom. That isolated hydrogen atom can fly off into space. Over a span of billions of years, Mars has lost a lot of hydrogen, and that translates directly into losing a lot of water. Only the water locked deep beneath the surface is immune from this kind of loss. Comets are mostly water ice. Most comets originate from the Kuiper belt, out beyond the orbit of Neptune, and from the Oort cloud, even farther away. Comets can change course as they interact with the gravity field of planets. When they do, they sometimes end up in the inner solar system, near Earth. Asteroids originate from the asteroid belt, and they contain significant amount of frozen water as well. Asteroids and comets may have delivered most of Earth's water to the planet when the solar system was young. We can test this hypothesis by comparing the isotope fractionation of comets and asteroid water with that of Earth's water. Hydrogen has two commonly and naturally occurring isotopes with one proton, but either one or two neutrons. Other isotopes exist, but have a short half-life or are produced artificially. Hydrogen is the only element whose isotopes have different names in common use today. The isotopes with two neutrons is called deuterium. We can identify the isotopic signature of water using the deuterium-hydrogen ratio. The results vary among observations. For example, the distribution of isotopes on Vesta, the largest planetoid in the asteroid belt, has the same distribution seen on Earth. In contrast, the water vapor from comet 67P, a Jupiter family comet originally from the Kuiper belt, is significantly different to that found on Earth. A competing hypothesis for the origin of water on Earth, recall that all volatiles were originally stripped off by strong solar winds, is that it was released from its deep interior by volcanism. The gas emitted by current volcanoes are 50 to 60% water, 24% carbon dioxide, 13% sulfur dioxide, and 3% other volatiles. Intense volcanism following planetary formation, when the planet was much warmer than today, presumably provided Earth its fluid envelope. Water ice is present in the darkest and coldest parts of the moon's polar regions. These ice deposits are patchily distributed and could possibly be ancient. At the southern pole, most of the ice is concentrated at lunar craters, while the northern pole's ice is more widely but sparsely spread. Most of the water ice lies in the shadows of craters near the poles, where the warmest temperatures never reach above minus 150 degrees Celsius. Because of the very small tilt of the moon's rotation axis, sunlight never reaches these regions. Liquid water has also been found at the surface in direct sunlight in the sunny Clavius crater. Water may have been delivered to the moon over geological timescales by the regular bombardment of water-bearing comets and asteroids, or continuously produced in situ by the hydrogen ions of the solar wind impacting oxygen-bearing minerals. Astronomers have documented numerous icy worlds in our solar system. All of the gas giant planets, though primarily made of hydrogen and helium, hold significant stores of water vapor in their dense atmospheres. Jupiter's large moons Europa and Callisto are now thought to feature an ice veneer a few miles thick over much deeper encircling oceans of liquid water. This vast subterranean sea could host living microorganisms similar in size and complexity to bacteria found on Earth. Farther away in the outer solar system, Pluto and its companion moon Charon are water ice worlds. Pluto may also host an ocean of liquid water in its interior. Saturn's most distinctive feature is the magnificent complex of rings. What appears at first to be a continuous broad ring is actually a complex system of ringlets with a very dynamic set of moons and other complex gravitational interactions. The bright rings are composed primarily of tiny ice crystals in a surprisingly thin sheet. And all of Saturn's moons have large quantities of water ice. For example, water escaping Enceladus rains on Saturn. Every second, 250 kgs of water rains off Enceladus. Some of this water is lost into space. Some freezes on the rings, or perhaps falls onto Saturn's other moons, but a small fraction does fall on Saturn, explaining the small concentration of water on Saturn's upper atmosphere. This is the only example that we have of a moon affecting the chemical composition of its parent planets. Titan is the largest moon of Saturn and is the only place besides Earth known to have liquids in the form of rivers, lakes, and seas on its surface. These fluids are not water, but liquid hydrocarbons like methane and ethane. Titan is 50% larger in diameter than Earth's moon and 80% more massive. It is the second largest moon in the solar system after Jupiter's moon Ganymede, and it is larger than the planet Mercury. Titan is known to hold large amounts of water in its deep interior, which is covered by a thick layer of water ice. This review shows that water can be found in many places in the solar system, and our understanding of stellar nucleosynthesis points to water being ubiquitous in the universe, appearing with supernovas along with common planet-forming minerals. Hence, there is no limiting factor for life to spread around the universe. It is likely that life appears elsewhere in the solar system in the form of microbial organisms. In other stellar systems and other galaxies, it is likely that life took form as well. With 100 billion galaxies, each with 100 billion stars, each with about 4 planets on average, and each with potentially 1 or more moons, there is an extraordinarily large number of places where life can root, and even where intelligent life can develop. A reason why we haven't heard from other intelligent life beings is that the universe is very large, and it takes a long time for any message to traverse the interstellar space and finally reach us. We also need to be around in the right time to hear it. Given that the solar system was created late in the universe, when it was already 9 billion years old, and given that it took 4.5 billion years to create intelligent beings on Earth to develop the technology for space communication, we may have missed the message. Or the message is still on its way. In 1977, we have sent a message describing human civilization, a sort of time capsule, on board the Voyager spacecraft. The space vehicle has now escaped the limit of the solar system and is zipping through outer space. The message is intended for extraterrestrials sufficiently advanced with spacefaring civilizations.